Okay, so the next main question type I'd like to talk about is these stable versus unstable points, and we can call them critical points or equilibrium points. I've kind of been calling them both. Um, so this is like 9.1 and 9.2, I think. Is that right? Let me just see. Yeah, yeah. But I would say mostly this is 9.2. Um, so I can give you a problem. I have an example down here, and what I might ask is the following: to find all the critical or equilibrium points, or I might just tell you what one of them is and then have you investigate that one. But either way, you'll have to characterize either all of them or the one of them that I tell you to focus on. You'll have to characterize it as one of the following. Now, in the book, they go into more detail than what I care to do. In the book, they have a lot of things like stable but not asymptotically stable. They have uh, more categories of points like saddle points or spiral points, etc. Um, as far as I care, I would just say there's two types. There's stable or unstable. Um, for the ones that we're calling stable, you would also be correct if you said it's asymptotically stable. I don't really care whether you say it's stable or asymptotically stable. As far as we're concerned, for the problems that we're going to be talking about, they're the same thing. Um, so stable just means that all the eigenvalues of the Jacobian have negative real parts. Unstable means that one of them has a positive real part. We did talk about what happens if all the if like the eigenvalues have the real part is exactly zero, then this test is inconclusive. Um, I'm not going to give you an inconclusive one on the test because I just want everything to be conclusive on the test. Um, so, right, you just have to find the eigenvalues of the Jacobian, and if all the real parts are negative, then you say stable, and if any of them has a positive real part, you say unstable. So, as far as we're concerned, that's all you need to do. So, yeah, I like these problems because it sort of showcases a lot of skills. The first thing you have to do, of course, to find the equilibrium points. So I'm just going to start working on this example. We have this nonlinear system, and the instruction is to find and characterize all stable or equilibrium points. So the first skill that this showcases is you have to solve a system, and this is a nonlinear system. And, in general, this can be hard. Of course, I'm not going to be too hard on you for this. There's a number of things you can do, like I can just solve this one for y. You want to be careful when you do this. We had a quiz where you had to find all equilibrium points, and I think there was something like this, and several people just said y equals 1, but you want to find all solutions, so it's y equals plus or minus 1. Once I know that, I can plug that in here and get x. But I have to do each one separately. If y is 1, then I get x cubed minus 1 equals 0. X cubed equals 1. So x would just be 1. X isn't plus or minus 1 here. The cube root of 1 is just 1. It's not plus or minus 1. On the other hand, if y is negative 1, the other possibility, then I get x cubed plus 1 equals 0. X cubed equals negative 1, and I would do the cube root of that, which would be negative 1. So it looks like when y was positive 1, I got x was also positive 1. When y was negative 1, I also got x was negative 1. So we got two critical or equilibrium points. So now let's characterize them. Say 1, 1. That means we have to find the Jacobian. So the Jacobian in general is a function of both x and y, and it's just this matrix of partial derivatives. So I go partial of this with respect to x. Actually, this doesn't involve x at all, so the partial derivative would just be 0. And then partial derivative with respect to y would be 2y. And then I move down here, partial derivative with respect to x would be 3x squared. Partial with respect to y would just be negative 1. Of course, we're characterizing this point, so I'm going to find j of 1, 1. So j of 1, 1 is 0, 2, 3, negative 1. And really what I care about is the eigenvalues of this. So this would give me negative lambda times negative 1 minus lambda minus 6. So this would give me lambda squared plus lambda minus 6, which is lambda plus 3 lambda minus 2. So I get lambda equals negative 3 and positive 2. And they were both real. One of them was negative, but the other was positive. So I would say unstable. If they were both negative, then I would say stable. Okay? So let's do the other one. Negative 1, negative 1. J would be, let's see, so I'm plugging it in here. So 0, negative 2, 3, negative 1. Find the eigenvalues of that. Oops. Okay. This time it's plus 6. So this is lambda squared plus lambda plus 6. And now I'm having trouble thinking of how to factor this. So maybe let's use the quadratic formula. Negative 1 plus or minus b squared minus 4ac. And actually right here I can see what's happening. It is going to be complex. I do see a square root of a negative number here. So what do I care about from this point on? I care about the real part. If the real part is negative, which it is, the real part is going to be negative 1/2. Because this, this is negative 1 plus or minus root 23i but I hardly care about this imaginary part. I care about this real part. So the real part of actually both eigenvalues, because the two eigenvalues are the plus and the minus, but the real part is the same. The real part of both of them is minus 1/2. So that's negative, so that's stable. Oops, the other side of this piece of paper had irrelevant stuff on it. Yeah. Yeah, so I guess there's not too much more to say about that. We found them and we characterized them, so we'll move on to the next video.